Next speaker is Yu-Fang Chen, who's going to be talking to us about verification.
Thanks. Yeah, I'm Yu-Fang Chen, and I'm here to present our automata-based approach for quantum circuit program verification. I will use these 20 minutes to introduce you these 4 papers. I hope I can. Okay, so this is our view of a quantum state. So it's a tree view. So the leaf are the amplitude and the branch are the basis. And this is a view that the quantum simulation people often take. So they use a tree to denote the state, and then the gate will update one tree to the other tree. And of course, they don't really store the entire tree in the computer because this will be like invisible. So they will have a very they use decision diagram to store a tree in a compact manner. That's what they did. And the problem here, this is actually the initial point of our research. So in classical verification, we also use VDD to encode the state, but we use VDD to encode the set of states. But now in quantum, VDD is only one state. How to do the set of state? Because we need a set of state to do the verification. So this is a basic setting of a partial correctness verification. So we have 2 predicates, precondition and postcondition. Each predicate characterizes a set of state. We want to check whether all states from P after executes S end up with some state in Q. So we need something, if we want to do this automatically, we need something like BDD for quantum to do this kind of verification automatically. So this is so our idea borrows from automata theory. So in automata, we use regular language, or let's say automata, to capture a set of strings. And there's another version of automata, they call it tree automata, or regular tree language, can capture a set of trees. So because this is somehow a standard model to capture a set of trees, so that's the beginning point. We think, okay, let's try tree automata to capture a set of quantum state. And based on this, we have to create the automatic verification framework. So that's it. So we use tree automata PQ to encode the precondition and postcondition. And we develop algorithms for each quantum gate to compute, let's say, the set of states from P after execute Hadama. And then we also have algorithm for control NOT and everything. So we just do the algorithm one after the other. Then at the end, we can get the set of state after reachable after I run the circuit. Then I check whether all of them are in the postcondition by running a standard tree automata language inclusion algorithm. So that's our basic framework in PLDI 2023. 23, right? Yeah, so that's the basic idea. And you must be curious that, okay, what kind of property we can do? Show you a few examples. So this is a Brenston Bazzani algorithm, but with multiple oracles, like with all possible oracles. So this shaded part is the oracle circuit. So we feed from the input the secret string known by the oracle. And the goal of the algorithm is, the other part is the algorithm. The goal of the algorithm is to find the secret. So we begin with this set of state, like all possible secret, like all possible Boolean strings, and then the working type initially is 0. This is the precondition. And we want to check, after I run a circuit, all the working type found the correct answer. So in order to do this, we need a set of state. And if you use simulate, you can also do this with simulator, but you need to run exponentially many runs to check it. Another interesting example is actually using set of states or vectors as pre and post condition can be very expressive. I have another example. We can use this to capture whether 2 circuits are equivalent. Circuit equivalent can be reduced to check whether a circuit is identity. And how to check one circuit is identity? It's enough to fit in 2 to the power of n, this many linearly independent vectors. If all of them, they can go back to themselves because of linearity of the quantum circuit. We know that this circuit is identity. If we fit in, we have a circuit, we have a matrix 2 to the power of n times 2 to the power of n. If we fit in like multiply it with 2 to the power of n, this meaning like a linearly independent vector, and all of them can go back to themselves, then we know that this circuit is identity. This is the way we use to check identity. And we have some specific set of vectors that we use for checking identity, because this can be encoded in a linear-sized tree automata. So we have 2 to the power of n, this many vectors, but the corresponding tree automata size is only linear. I'll show you a simplified version of this. So here, give you a more concrete example, like what a tree automata looks like. In the case of bounded number of qubit, tree automata is actually decision tree in addition with non-determinism. So this is a tree automata, and if you only read the red part, this is the decision tree, binary decision tree. And in the node P, you can see that we have 2 possible choices. If you pick a blue one, you get another decision tree. So this is actually one way to encode multiple decision trees in the same structure. So recall that the advantage of decision tree is that if inside one state you have some common structure, then you can merge them. Now, using this automata, you can also merge similar structure across different states. So we use this to do basically create a structure that allows us to do simulation of multiple states simultaneously. And we use this to create a symbolic verification framework. So this is the basic version, basically BDD plus non-determinism. And in this kind of example, we can use, this is only, we have roughly 10 state transitions, and you can encode 8 different computational basis states. And if we repeat the structure of this layer, like 3 more transitions, we get one more qubit. And we can use actually a linear number like 3n plus 1, because for each more qubit, we just need to add 1 more layers to encode 2 to the power of n, this many basis state. So this can be very compact. The technical detail probably is not that important, but I hope I can somehow convince you that it can be compact. And the reason is that you can use not only the shared structure within one state, but also across different states. Yeah. So next, give you a little bit of feeling of how we do quantum gate. So start one, this automata. If you want to do X gate, it's very easy. You just look at all the transitions labeled X1, and then swap left and right. The dotted one is the 0 branch, and the solid one is 1 branch. You just swap them. Then you get the X gate. And ZST gate, essentially what they need to do is to multiply the right subtree with a constant number. These are rotation gate. So what they need to do is to multiply the right subtree with a constant value. And we cannot directly update the amplitude value here, because this amplitude value may be shared by different trees. So maybe this is the right tree of some people, right amplitude of some people, but this is the left amplitude of the other people. So our algorithm actually need to duplicate the structure. And in the duplicated structure, we multiply everybody with C, and then we rewire the right tree to the duplicated one. This is our algorithm for this kind of ZST gate. And there are, of course, some more other gates, construction of other gates. We will not include in this. Just give you a flavor of what our algorithm will look like. And after this kind of construction, also it looks like the state space will be doubled. We will run automata minimization algorithm to make it compact again. So automata has state space minimization algorithm. So that's the basic framework, published in 2023. And later, in CAF 2023, we have an extension. So in the previous version, all the tree leaf, you have a constant value. But now, we use variable in the tree leaf, and then perform symbolic execution over the gate. This give us a lot of additional power. For example, in this framework, we can verify that after finish the global search, the amplitude value is bigger than 90%. We don't need to have exact value there now. previously, it's very painful. My students spent like one afternoon to compute what is the MT2 value after running over. Yeah, but now we can write bigger than 90%. And also, we can use this to verify after execute the Gover iteration, the probability of finding the correct solution is increased. We can verify this kind of property by basically a combination of automata and symbolic execution. So here are some experimental results to show you like how it behaves. For the Gover iteration example, we can verify things like 200 qubit in 17 seconds. But this is because Gover's algorithm, they have very spatial structure. Like one branch has high value, the other branch has very good value. This is perfect for decision tree. Yeah. So this is not really work for everything, but for Gover, we can do it. And there are some more ideas. Like we can play a lot of magic in the tree leaf. Like if we combine, we talk about combining tree leaf with symbolic execution. We can also try it with abstract interpretation, they say. So the tree leaf now is an abstract domain. And why we want to do this? Because if we don't have any abstraction, then everything we can do is what classical computer can do, because we compute the exact value. So we can never go beyond things with quantum advantage. We cannot go beyond things with quantum advantage. The only chance is that we do some kind of abstraction. And using abstract domain in the tree leaf is one thing that we are thinking of. We are not there yet, but I think this is full of potential. And one more thing. So actually we can do, so we only talk about BDD with non-determinism, but tree automata actually has loops. So if we add loops, what will happen? So we can encode things like any number of zero states. And then we can do verification starting from this kind of set of state. We can apply any single unitary gate to this and get the next automata. Sounds good, but what we cannot do is apply Hadamard to everybody. So we are not there yet. We can do some kind of parameterized circuits, like we apply C0 to everybody. We can do C0 1, 2, 2, 3, 3, 4 to the end. So we can verify, let's say, GHZ circuit of any number of qubit. And we also have diagonal Hamiltonian simulation circuit and 2 circuits related to quantum chemistry. So we can do this kind of example, but I mean, we cannot do Hadamard O. So you see, this is very limited. So we are not there yet. Okay, the last thing, quantum program verification. This is in TACAS this year. So previously we have quantum circuit, but in quantum program we also have branch statement and then loop statement. So in this branch statement, you need to. It says that if the major value of first qubit is 0, then I execute this loop body, and the same for loop. If branch, and then for loop, if the measurement value is 0, then I can execute this loop body value. I will show you how we handle this. So the key is to handle measurement. So let's see, starting from this state, if we measure the first qubit and the value is 0, what happens is that now we know the value of x1 is 0. There's no chance that the x1 be 1. So we need to update the probability of the right subtree to be completely 0. But the problem is that this is not there yet. We still need to normalize the amplitude value because this is not the quantum state. And you see that in automata, the structure of all the states are shared. Now, if you need to normalize all the state, it's a nightmare. The only thing you can do is probably to uncompress everybody and to normalize each of them separately. I mean, this is infeasible. Our way to doing this to do this is that we don't normalize. Instead, we go back to modify the language inclusion algorithm for tree automata to allow the match of one tree with another tree with different up to a scalar. So this is what we do. We have a modified version of tree automata language inclusion algorithm to allow up to scale inclusion. So with this, we can handle measurement. For loop, we require the user to provide a loop invariant in the form of automata. And if this is provided, then we just need to check whether from precondition, before we enter the loop, it's a subset of the invariant. And started from loop invariant, if you enter the loop, major 0, and then execute the loop body, it's again fail into the invariant. And from the invariant, if you leave the loop, it's in the post condition. We'll need to do these 3 checks. All this can be done fully automatically. So this is what we can do for quantum program. So we are there. So this is 2025, and then we already managed to present 4 papers in these 20 minutes. And we have a lot of things that we want to do more, like we want to find better abstraction refinement, because otherwise we have no hope to do examples that is really exciting for quantum. And we want to do automatic loop invariant synthesis, because then we can make everything automated. And we want to do probabilistic reachability also, because now what we can check is that all the state need to be filled within the post condition. But we can probably check something that is more interesting, like 90% of the state is in the post condition. And where the probability comes from in the measurement. So far, we just threw away all the probability. Like actually, there's a chance there are some probability that the major amount to be 1 is the major value is 0, and some other probability measurement value is 1. We didn't make use of this probability. We just in this framework we just want to check that everybody is really within the post condition. But there's a chance to do this by reduction to parameterize the Markov chain. This is all these are ongoing work. Okay, so I want to do the final advertisement. So with Renzhou Tao from University of Maryland, we plan to organize a quantum workshop also in CAF. Because it's very nice to have a quantum workshop. Like, you need to spend 5 minutes to talk about what is qubit. I can really go into point immediately. So we think we want to have this also in CAF. And yeah, so this is the QR code for the website. And CAF will be in Croatia, Zagreb this year. Croatia could be a nice place, very beautiful. So, and we need the help to like participants help us to make this really happen again, really happen. Yeah. So, yeah, that's it. Final thing. So if you are interested in this direction, we have a lot of opening, like postdoc and the collaborators. We can invite you to visit us. Yeah. So, if you are interested, you can scan this QR code, find the information to contact. Thank you very much.
Questions? I will ask a question while you all think about it. So do you have a nice characterization of when the tree automata representation doesn't compress a quantum state?
Yeah, they are.
Right.
Right. After QFT, if you use like basic tree automata, because after QFT, all amplitude will become different. So you have no chance to make it compact. But we are investigating new symbolic formalism. You can imagine that if we do a 2-qubit QFT, like we have state ABCD after QFT, and if you allow me to use I to denote the corresponding empty basis, then all the tree leaf can be represented as A plus B omega I plus C omega 2I plus D omega 3I. Like they have the same symbolic representation. So I mean, this is more like this kind of like a battle between, okay, I cannot do this, I have another new approach. So I think the catch will be we really need to have, and in simulation community they have different kind of like data structure, like tree-like data structure, like tensor decision diagram, for example, to describe describe state, and all of them we are thinking of leaving them to automata. Yeah, and then they can probably handle different kind of problems. So that's what we are thinking.
Excellent. Thank you. Any further questions? Oh, right at the back, of course.
Thank you for great talk. And I'm wondering if how can we represent the mixed state. So I imagine that we can represent such states if we build a ability of the result of the measurement history on the top of the tree automata. Is that it makes sense?
So we can, of course, use ability to represent a matrix by using the branch to simultaneously record the x and y axis, but we choose not to do it. And then, so our workaround is like when you do the measurement. After you do the measurement, like if you, the reason you need to have mixed state is that you want to have the probability of left branch and right branch mixed together. But we can actually handle them separated. Like we know, we can imagine that we are building a Markov chain, and go to a left, we have some probability, and then this is the left tree, and then go to a right, there's a probability, there's another tree. Of course, now we have a set of trees, so probably this is not a fixed probability. This is a range, like a maximum least, minimum least. But this, if you want to do analysis, this is exactly the so-called parameterized Markov chain problem. And even like tool is implemented there. So haven't done it yet, but this is something that we are thinking of to do probabilistic retributivity. Like we try to avoid using mixed state, but in this way.
Okay, thank you.
Okay, and I think with that we'll wrap up the session. So thank you very much for the talk.